Hello everyone, this is Akhil Ajinkar, working as assistant professor in Computer Science and Engineering Department, Jhulelal Institute of Technology, Nagpur. So today we are going to discuss the topic of computer architecture subject, that is restoring division algorithm. So when computer is going to perform division operation, in that case whatever operation is performed, it should be in a binary. So to perform binary operation, there are multiple algorithms are used, but in that one popular algorithm is restoring division algorithm. So now today we are going to discuss about the example of restoring division algorithm, how we can perform the restoring division. So now you can see on screen the example of restoring division. So this is the actual division of 8 divided by 3. So what is the dividend here? Dividend is 8. Okay. Dividend is 8 and divisor is 3. So what is the result? Result quotient is 2 and again remainder is 2. So this should be the answer. So by performing this operation 8 divided by 3 division, by using restoring, how we can perform, we will see on next slide. So this is you can see before that you can see this is the operation, and you can check the last result here. So this is the remainder portion and this is the quotient portion. So both are 2 in decimal and 2 in binary, you can see. But how we can perform these cycles, cycle 1, cycle 2, cycle 3 and cycle 4, and again what are the steps to perform in one cycle and second cycle and third cycle and fourth cycle. So there are multiple steps has to perform, and when it should be performed, or when it should be avoid. So we will see in next slide. So our operation is 8 divided by 3. 8 divided by 3. So what we need to perform? We need to perform 8 divided by 3 as an example of restoring division method. Okay, 8 divided by 3. So what is the binary equivalent of 8? It is 1 0 0. Okay, and then what is the binary equivalent of 3? 0 0 1 1. Okay, so this is the binary equivalent of 3 and 8. So now to perform, you can see in this solution there are 4 cycles. So, so we will discuss here how to perform the first cycle for performing division in restoring method. So for first cycle, initially we take 5 zeros in binary. Okay, this is the adjustment required for to perform division operation, and suppose consider that it is present in register A. Okay, and again in register M we will take the dividend. What is dividend? Dividend is 8 and 100 is the equivalent of binary equivalent of 8. Okay, so initially we take these 5 8 in both are in different register. 5 zeros are in register A and 1 000, that is our dividend, it is in register M. So now we'll perform the second operation for cycle 1. So this is first operation is second operation is shift. In that case, we need to shift all the bits, all the bits 0, 0, 0, 0, and first bit of this M is shifted to the last bit of register A, and here are remain three zeros, and one space is blank space. So we perform next steps to get this last Q0, means this is the quotient, this is the quotient, and quotient last bit is Q0. So what should be the value of Q0? We will perform for this, we will perform the next step. The next step is subtract, subtract. So how we can perform the subtract? We can see, we can consider this is X, this is X, and from this X we need to, from this X we need to subtract 3. What that is our divisor. We need to subtract 3, that is our divisor. But if this is X, means X, what we need to perform? X minus 3. So again this operation is equivalent to what? X plus minus 3, x plus minus 3. So there is a mechanism that we can represent the minus 3 in binary. So for this, there is a mechanism we can write minus 3 in binary. We can represent minus 3 in binary. So in that case, how we can represent the minus 3 in binary? So we need to perform 2's complement. Okay, we need to perform 2's complement. Suppose this is our 3. What is the value of 3? 0, 0, 0, 1, 1. It should be in a 5 bit. That's why I add 0 in front of the number. This is my 3 in binary. So now I want to perform 1's complement. Okay, 1's complement. For 1's complement, write the opposite bit 1, 1, 1, 0, 0. If there is 0, then write 1. If there is 1, write 0. So this is 1's complement. And for 2's complement, add just 1 in binary. So what is the result? Triple 1, 0, 1. So this is the representation of minus 3. Okay. Now if we get the representation of minus 3, now we need to perform only addition. We need to perform only addition. You can see here we need to perform only addition. So whatever we get, whatever we get, okay. So whatever we get from shift operation, we need to perform addition with minus 3. Okay, with minus 3. Why minus 3? You can see here. You can see here why we perform addition, because it is very easy to perform addition in binary. Okay, it is very easy to perform addition in binary. So how we can perform the addition? So we just write out the equivalent of minus 3. So this is our equivalent of minus 3. Now in that case, we perform the addition operation. This is 0, 1, 1, 0, and then carry 1, means it's 1, again 1, again 1, again 1. So this is the answer of subtraction. So the first bit of answer of subtraction will decide the value of Q0. Value of Q0. Okay. Write down the first bit, opposite bit of first bit of subtraction operation. So if the first bit is 1, if the first bit is 1, then it should be 0. Okay. And if the first bit is 0, then it should be 1. Okay. Write down the opposite bit of first bit. So this operation is called as set Q0. So we are setting the value of Q0 by getting the result of subtraction. Result of subtraction here, which is the before earlier step of set Q0. Okay. Now the next step. If if the result of if the result of subtraction we get first bit is 1, then we need to perform restore operation. Restore what? Operation. So in that restore operation, whatever you subtract from the initial bits of A, we need to add it. We need to add it. So what we perform uh, in subtraction? In subtraction, we perform the in subtraction we perform the subtraction um, by using 3. Subtraction by using 3. Now we add the 3 again. And now we add the 3 again. And that is the operation is called as restore. The operation is called as restore. So we get the original value before perform subtraction. So this is the original value. So this is the original value you can see. Okay, this is the original value, and from that we are subtracting 3. We are subtracting 3, and so after subtracting we will get this, and result of this, in that we are adding the same number 3. So what we get? We will get the original number. We will get the original number. So result of this is the result of cycle 1. So this is the result of cycle 1. So this is the result of cycle 1. So what is the result? 0, 0, 0, 0, 1. 4 times 0, 1. This is the remainder portion. And 4 times 0 is which is quotient portion. But we can see the previous answer. After completing cycle 1, we will get 4 times 0 and 1. You can see this result. Okay, and this one. So this is the result of cycle 1. Now we will perform the same operations. Now we will perform the same operations in cycle 2. In cycle 2. Now we perform the same steps in cycle 2. So the result of first we will copy the result of cycle 1. Cycle 1. First, we will copy the result of cycle 1. That is 4 times zeros, 1. Then again 3 times 0 and in bracket, in square bracket, 0. Okay, so this is the result of cycle 1. Now we will perform shift operation. That is our first operation for cycle 2. 0, 0, 0, 1, and then first bit of M register is shifted to the A register. And what will remain here? Here is double 0 and then bracket 0 and then again blank bracket. Okay. Now again we need to perform subtraction operation, which is our second operation. In subtraction, we what we need to add? Minus 3. If we add minus 3, then if we add minus 3, then we will get the result. We will get the result. So what is the result? Result here is, okay. So this is the result of subtraction. Then by using this first result of subtraction, first bit of result of subtraction, we can decide the Q0. So the operation is called as set Q0. So according to this, it should be 0. Okay, if the first bit is 1, then Q0 is 0. And if first bit is 0, then Q0 is 1. Okay, now, we are getting 1 in first bit. So we need to perform restore again. We need to perform restore again. So 0 0 0 1 1. Okay, 0 0 0 1 1. So perform restore operation, what we get? We get 0 0 0 1 0. This is the addition. Addition of this plus this. Okay. So this is the result, and this is the result of mm, remainder, and this is the quotient. So there is one question, why we need to perform 4 cycles. So we perform 4 cycles for what? We are getting the 4 brackets in quotient. 4 bracket in quotient. So whatever the value of this 4 bracket will become the quotient of our result. Result quotient. Okay. So this is the cycle number cycle number 2. Okay, this is the cycle number 2. Okay, wait. This is the cycle number 2. This is the cycle number 2. Now we will perform the cycle number 3. So first, before perform the cycle number 3, we get wait, we get the result of cycle number 2 to perform cycle number 3. This triple 0 0 1 and 0 0 0 and 0. Then we will perform again shift operation. Okay, double 1 0 0 0, and then 0 0, and after perform shift operation we will get last blank bracket, that is Q0. So for setting Q0, we need to perform for first subtraction operation. So this is the representation of minus 3. This is the representation of minus 3. Okay, so what we get? We get result 1 0, again 0 0 0. This is the result. Okay, then we need to set the Q0. Same operation which we already perform in cycle 2. This is set Q0, that is 1. Why 1? Because the first bit is 0. Write the opposite of first bit of result of subtraction. Then we are getting here 0, means we don't need to perform restore operation. We need to perform restore operation only one when we are getting the first bit is 1 of subtraction operation. In that case we are perform only restore operation. So in this cycle 3 we don't need to perform restore operation. This is our last result. Okay, now we will perform the cycle number 4, that is our last cycle, that is our last cycle. So now what is the result of cycle 3? 4 times 0 1, and here first 0, then in bracket 0, then again in bracket 0, then in bracket 1. Now we perform again shift operation. 3 times 0 1 0, then here 0. This first bit is shifted to register A. This is 1 and this is our blank bit, that is Q0. To set this Q value of Q0, we need to perform first subtraction operation. In that subtraction operation, we need to write -3. Okay, so this is the result of subtraction. And the Q0 is depending on the first bit of result of subtraction. So what will be the result? 1. So that's why we need to put here 0, opposite bit of first bit of result of subtraction. And again we get first bit is 1. So in that case we need to perform restore operation. We need to perform restore operation. In that restore operation, we need to add 3 in that, the result of subtraction. So what we get? 00010. This is the result, and this is we call remainder, and the quotient is this is our quotient. So what is the remainder? Remainder is 2. Again, it's in binary, it is in decimal 2, and quotient is 2. So you can see the result. You can see the result. So this is the final operation. We can see here the quotient and the remainder both are 2. In case of the problem 8 divided by 3. So this is the example of binary division in by using restoring division algorithm. So this is about the binary restoring division algorithm. Thank you very much.